Okay, we are going to get started on homework for part D. The question is derive an expression for the steady state absorption flux of a gas A into a liquid film of thickness beyond which the concentration is approximately 0. Once absorbed into liquid A is consumed by a first order reaction with a reaction rate K. Species A has a concentration of C base AI at the vapor-liquid interface that can be assumed to be dilute in solution such that the diffusion can be described by a fixed diffusivity of D with no convective contribution. So I just wrote a couple things again, down, being that at steady state, our film thickness, our liquid film thickness is equal to, I don't really even know what this is, gamma maybe, that variable. Reaction rate is equal to K, and our species A concentration is equal to CAI. And then I also put for a first order reaction, our negative R is equal to our reaction rate times our species A concentration, because we will be using that later. So what we're gonna do now, actually cut like where I just started talking, and then I'm going to jump back in. Okay, now we're actually, to get started, sorry, I had to cut for a second. We're going to start with Fick's law, so I'm just going to write Fick's law. And then, that's supposed to be an error, oh. So what we're going to have is we're going to have our NA evaluated at Z equals 0. And that's going to be equal to our negative D from A to B, multiplied by our dCA over our dZ. And then we can also write a time dependent version of this exact Fick's law mixture thing that we did here. And then we can make it time dependent. It's going to be our dCA over dt, and that will be equal to our D of our NA, and that's also going to be negative, over dZ, and then plus our R that we have to carry over. So that R up here is now, that's what we were using it for basically, because it makes things a little bit simpler later. So this term right here is equal to 0, and we just know that when Z equals 0. So we can say that's 0, and then we'll have everything on our right basically. So let's rewrite that, adding our first order reaction into it as well. So we'll have 0 is equal to negative, actually it will be positive since we're adding this negative R in. It makes the first term positive, so it's going to be dCA over dt, and then it'll be minus since negative KCA. And this is for steady state. So that's what we have now. And to get further, we're going to have to take the derivative of this. So when we take the derivative, we're going to get 0 is equal to negative D squared over CA over DCA, DZ squared. And then we'll get minus K over dA B, and then multiplied by our C. So finally, what now we have to do is solve for our C value, and in order to do that, we're going to have to make up a unit. But the unit we're going to make up in this case, since we need C, is going to have to be, we'll just call it M, and it's going to have to be equal to the square root of K over D from A to B in order to isolate C. So when we plug that in, we will get, when we plug our M in, we'll get D squared CA over DZ squared is equal to our negative M squared C. So this is kind of similar looking to a differential equation. So now we're going to have to use differential equations to get further, and we're going to do that using hyperbolic sine and cosine, and we're going to have to do it at two states, at when our z is equal to 0 and when our z is equal to our liquid film thickness. Okay, we're going to get started at z equals 0. So when z is equal to 0, we will have our, since we gotta find our CAI value, that will be equal to A, and then we gotta use our hyperbolic sine and cosine rules, so we're gonna get e to the mz minus e to the negative mz over 2, and then we need to do it one more time. Sorry. And then we know that this term here will just go to 0 because we will get 0 in the numerator with our Euler's, and then when we go here, we'll just get e to the 0, e to the 0. So we'll get e to the 1 plus e to the 1, which is 2 over 2, which is 1, so we'll just get b. So this can just simply be simplified to CAI is equal to b. And then finally we gotta do z when it's equal to our liquid film thickness. So we're going to get, it's going to be very similar to the above one. We're going to get A is going to be equal to negative C AI, and then times our cosine, hyperbolic cosine, times M, and that will be over sine hyperbolic, and then same quantity. Okay, so now what we're going to have to do is we're going to have to plug in this CAI value into the A, or our second thing that we did here. So this is going to be a lot. So we're going to have C. So we're going to have C is equal to negative, oh my gosh, A, well, we don't need A. Hold on. It's equal to C, negative CAI, cosine HM gamma. I think that's a gamma. I need to figure that out because I've been using it all semester. Sine H mz plus CAI cosine H, or hyperbolic mz sine, HM gamma. Okay. And then that will all be over just one little term, hyperbolic sine of M gamma. Okay, and then when we simplify this value, we'll get C is CAI. When we pull it out of the quantity, we'll get sine hyperbolic times M gamma. Oh, sorry. I don't even know where I got that. Z minus gamma over the thing in the denominator. Okay, so now what we can do at this point is we can plug this value back into our Fick's law. But first we need to derive this term. And when we derive it, we'll get CAI over, sorry, we need to, with respect to Z, will be negative MCAI cosine H. And then that will be M gamma sine H M gamma. Took a little bit. Okay, and then we can kind of finally we just need to add that back into our original expression here. Hopefully that copied over. It kind of was okay. So just kind of add that back in. So when we evaluate NA at Z equals 0, we'll get the D and then AB, so it'll be negative M CAI cosine H M gamma over sine H M gamma. So yeah, we need one more. So there we go. So we basically was just deriving the expression like it says, using differential equations, and we did this with no convective contribution. So